I would like to introduce Ton van den Bogert. He's giving a tutorial on musculoskeletal modeling, and I see you're getting ready to start to follow the tutorial on the computer, which is very nice. We got 2 more votes for the poster, so I would love to get some more votes by lunchtime. So if you have time during lunch to give us a vote, would be great. And I would like to hand over to Ton.
Okay, let's get started. So if you have MATLAB installed on your computer and you have the... Is it on? Okay. If you have the flash drive and you have MATLAB installed, you should be able to work on some of the examples that I'm going to show. And I'd like this to be quite interactive, so if there are any questions that come up, please interrupt me, as I'm sure you're used to doing anyway. First of all, a little bit of introduction. My background is actually in physics. I did my doctoral work on animal locomotion, and I did a lot of modeling and experimental work on horse locomotion. And then I went into human sports biomechanics. I was an assistant professor at the University of Calgary. Then I went to the Cleveland Clinic in 1998. Was a researcher there for 12 years. And about a year ago, started my own company, which is Orchard Kinetics. And I provide all sorts of computational biomechanics services to collaborators in academia and also to companies who need software or need research projects done. I also sometimes deliver software that gets embedded in products. So if you're looking for a collaborator on musculoskeletal modeling, typically I would help you with your grant proposal, and then I end up doing a subcontract, and that usually ends up working quite well. This is just the copyright that tells you that you're free to share all of this material as long as you give credit and you don't ask people to pay for it. Marco Ackerman helped me a lot in the... is there a pointer somewhere? He helped me with the development of the tutorial and testing of the software, and then I should also acknowledge the funding from the NIH for various parts of this work. So I'm going to talk a little bit about the elements of musculoskeletal dynamics, and mainly I think muscles for this audience would be of interest because I haven't seen much on muscle dynamics yet. Multi-body dynamics I'll do very quickly, and contact. Then we're going to do some MATLAB simulations of simple models. The first one is an isolated muscle contraction, which is very similar to the type of experiments they do on isolated muscles in animals to identify muscle properties. And then the second one is a 1 degree of freedom knee extension, where you have a muscle model and you have a skeletal dynamics component as well. And then you can see how they interact. And then finally, there's a dynamic model that's suitable for gait and walking simulations that I've provided on the flash drive. And we're going to talk about the system dynamics and do some interactive work with that. So if you have your flash drive, you can. There's a folder called Tutorial 2.
Can I ask a
Yep.
general question?
Yep.
Let's just say we're totally lazy and we just want to watch.
You can do that too. Sure.
Are we going to see everything that you're going to have us do?
Pretty much, yeah. So you've got these 2 folders, and just make sure that they're on your hard drive somewhere. It's probably best to keep the original on the flash drive untouched, so you always have that. And then let's first go to this tutorial folder, which has a PDF file that has this presentation on it, and then the 2 simple simulations. So, as an introduction, my reason for doing this, and it's, as I understand from Andre, why I was asked to present this, is that there is a need for dynamic models for simulation of movement and as a test bed for controllers and theories on motor control. And so I'm going to be presenting a dynamic model of musculoskeletal dynamics. I'm not going to be talking about controllers or about how to evaluate performance and how to optimize performance, just basically the modeling. The other application of models is then, of course, in optimal control. As we saw yesterday, you try to find open or closed loop controls that minimize a certain cost. So this is an example of the sorts of applications that people might develop with this model that I'm presenting. This is a neural control with rhythm generators and sensory feedback from the 1990s. And so here's a musculoskeletal dynamic system. In this particular work, they didn't pay very much attention to the musculoskeletal modeling, so the muscles were basically torque generators and did not have elastic properties and realistic properties. So if you wanted to redo this work with a more realistic model, you can use the one that I'm giving today. And another example is Geier's work with a reflex-based controller, which did have quite a realistic musculoskeletal model, and the one I'm presenting is actually quite similar to that one. And this is more my own area of interest, is optimal open loop control to predict human performance based on certain cost functions. And we published a paper last year where we did some very basic work on trying to figure out whether muscle activation squared or cubed is better, and whether there should be any weighting with muscle volume when you minimize the cost function. You get quite different gait patterns depending on which cost function you use. So the objectives is to understand the elements of dynamic musculoskeletal models, which are muscle, multi-body dynamics, and ground contact. And then you can use that to solve all sorts of problems. So first of all, muscle dynamics. I'm giving you two references here that I tend to use. The first one is Zajak's article from 1989, and the other one is a textbook chapter, which is more from the biological side, but also has very useful information about muscle properties. So muscles, just good to remind you that muscles is basically it's a piece of meat, and it's not as neat as an electric motor. So muscles are divided into bundles, fascicles, and then you go down to the lower levels. You have proteins, and the main proteins in muscle are actin and myosin, and they're arranged in these filaments that are overlapping. And then between the one filament and the other, you have a rotating head of the myosin molecule that actually powers the muscle contraction. And the little molecule that you see attaching there, it's the ATP, which gets turned into ADP, and that is actually a power source. So this is the molecular motor that's inside the muscles. It's good to at least be aware of that, because it's really the basis for all of the muscle properties that I'm going to be talking about. The first muscle property is activation dynamics. So you have a motor neuron that sends an electrical signal to the muscle, and then there's all sorts of chemical events that need to happen before these proteins start moving their motors. And this is typically modeled in musculoskeletal models as a first-order differential equation, where U is the neural excitation, so that's the signal that comes from the nervous system, and A is the active state. And then there's a rate constant here that depends on the activation. So when the activation is 1, the excitation is 1, you get this rate constant. And when the excitation is 0, you get the other rate constant for deactivation, and which is a little bit slower. Typically, I use 10 milliseconds for the activation and 40 milliseconds for the deactivation. And then if you control this muscle with a square wave signal, you get this rising part in 10 milliseconds and then the falling part in 40 milliseconds. And that's all based on experiments such as these, where you take an animal muscle and you stimulate it with a pulse train, and then you see what kind of forces come out. Of course, this force is not the actual chemical state of the muscle. There's all sorts of other things, but this is really what that is based on. The second part of muscle dynamics is the muscle contraction. And that has to do with this three-element model that is typically used. So the contractile tissue, these are the protein filaments, transmits the force through a series elastic element, and then there's also a parallel elastic element. This contractile element has the properties that come from these overlapping protein filaments, which are called a sarcomere. So the first property is a length-dependent capacity to generate force. There's one particular length of this contractile element, which we call the optimal length, at which it can produce the most force. And that's where the overlap is optimal. If you overlap less, then you have less space for these heads of the molecules to attach, so you get less force. If you overlap more, then you get compression, which counteracts the force generation. So there's this optimal length here. And then the second one is the force velocity property, which tells you that if you shorten the muscle, it gets less and less capacity to produce force. And typically at about 10 fiber lengths per second, you can no longer generate force. That's the maximal shortening velocity. So when a muscle is not attached to anything and you activate it, it will shorten at exactly that speed because it's unloaded. And then when you stretch the muscle, you get more force out of it, and that can be 50% more or maybe 80% more, and that levels off as you stretch faster and faster. So this is on the horizontal axis is length, and here is velocity.
Most people plot that.
Right, but I want to plot this as the derivative of that other variable. So, yeah, you're right. Mostly you see this one flipped horizontally. So you put these three elements together in an equilibrium equation, and it looks like this. You sum these two forces, you multiply by the cosine of this pennation angle, and then it has to balance the series elastic element. Then you put in all the different properties of the elements. So the contractile element force is the active state multiplied by a maximal force that it can generate. Then you have the length dependence and you have the velocity dependence. And then the parallel elastic element is just a nonlinear spring. And the series elastic element is also a nonlinear spring. And then for the pennation, there is a constant volume constraint that is typically used. Yes? This is muscle plus tendon, yeah. Yeah, this series elastic element represents the tendon, but also other connective tissue that's in series with the fibers inside the muscle. So that's typically lumped into one spring there, yeah. And the constant volume, that gives you a relationship between the length of the contractile element and that pennation angle. That comes from the fact that a muscle is, yes?
The two force length and force velocity curves,
yeah.
Are those tabulated or are there like any sort of characterization for them?
So both. You can find in the literature, you can find graphs of these that were measured. And I typically use analytical functions, so I use a Gaussian for this one, and I use hyperbolic equations for those ones. And I like to have analytical functions because then they can be differentiated and they're continuous. So that's just a choice. And really it's not that critical, I think, because if you look in the literature, there's a lot of variation in the details of these. As long as they look like this, I think it's fine. Then to get an explicit differential equation, you need to solve this for the derivative of the state variable. The state variable is the contractile element length because that's the only one of which a derivative occurs in the equilibrium. Then you get this nasty thing that involves dividing by the cosine of that pennation angle. That's one potential source of singularity, because if that pennation angle becomes 90 degrees, you're dividing by 0. That never happens in the real world, but it might happen in your differential equation solver or your optimal control while it's iterating, and then you have a numerical problem. I often just neglect the whole pennation and say that it's always 0. There are other potential singularities, for instance, when the activation is 0, or when your muscle fibers are at a length that they cannot produce any force, then you're also dividing by 0. And then there's a third one related to this force-velocity relationship, which isn't really invertible all the time. You see here, when the force is above 1.5 or below 0, there is no corresponding velocity. So it's not a perfectly invertible function. And then the way in this particular model that I'm showing today, I just eliminated all those singularities by adding a small amount of damping here. So that way the contraction velocity always exists no matter what state the muscle is in. It's also, yes? Just, yeah, it's just there for numerical reasons, so it just has to be small. But you do end up with a near singularity, and the smaller you make the damping, and especially because this is usually a stiff spring, or can be stiff. It's nonlinear, so it can be stiff. And then if your muscle is not activated, this is basically not there. And then you have very fast dynamics. That's one reason why I sometimes like to work with implicit models where you don't solve for this contraction velocity, but those are much harder to use. So I'm not doing that here. Yep.
Just a tiny question.
Yep.
Was it the addition of the damper that made it numerically stiff?
That's right. Well, because the damping is small. It has to be small, otherwise we're not having a good approximation to a real muscle. Yeah.
What about putting a mass in?
That's another way to do it. But then the mass has to be small and you have a similar issue. Yeah. And then you get second order dynamics. Yeah. So that was basically the whole description of muscle dynamics. You have two state variables, the active state, which is controlled indirectly by the neural excitation, and then you have the contractile state, which is the length of the muscle fibers. The multi-body dynamics is probably something that's familiar for most of you, but I'm just going to present it very briefly. So equations of motion can be written in this form, where you have generalized forces, and you have inertial term, and you have all the other terms that I lump into here, which are gravity and inertial effects and contact forces as well. They're all functions of the generalized coordinates and the velocities. Solve it for accelerations, you get the inverse of the mass matrix. And it's important, I think, to just mention that this mass matrix can be near singular, and that causes numerical stiffness. So very often in musculoskeletal systems, you have big masses and small masses all in the same model. So for instance, you have a finger here, and you can produce quite high forces, but the inertial terms in the equations of motion are tiny for those degrees of freedom. So you have a mass matrix that can be almost singular. So numerical stiffness is always an issue in a lot of models. Yeah.
What do you mean by numerical stiffness?
Oh, when you solve this differential equation, so if you want to simulate movement, then you have to integrate this twice. And because in this B term, you have very stiff elements. You have contact. In the torques, in the joint torques, you also have very stiff elements, which are the tendons. So you have very high stiffness here, and then you multiply that by a matrix that has very high eigenvalues and some very low eigenvalues, and you get numerical stiffness typically. And then what you have to do is a differential equation solver ends up taking very small time steps. And that's what's numerical stiffness. Contact is in walking is of course an essential part of the model, and you can model hard contact, for example, with linear complementarity constraints, which I've never done. I just know it can be done. I've always used deformable contact, and mainly that's because the types of scientific questions that I was dealing with, they required that. For instance, with the horses, we wanted to find out if walking on sand and walking on pavement gives you different forces in the tendons. Well, you have to have deformable contact models. And in sports injuries, we wanted to have the capability that people slip instead of just having a foot stuck to the ground. So I do deformable contact, and briefly this is how it goes. You define some contact points on the body, and then the position will be, with a forward kinematic model, you can calculate the position of each contact point from all the general coordinates of the model. So those are your joint angles, basically. And then the velocity is just a derivative of that. And then you make an elastic model for the normal force. And it can be viscoelastic, so it depends on the penetration and the velocity of penetration. And then a frictional force that depends on the normal force and the tangential velocity. And I won't go into details, but the equations that I'm using they're described in this paper. And here are some graphs that come from the Gait model that is on the flash drive. So I've just positioned this model vertically and then moved the hip up and down. And when the hip height is about 96 centimeters above the ground, you start seeing this contact force, and you go lower and lower, and you see the contact force go up. And so to get something like a full body weight, you need 1.5 centimeters of deformation. Yeah?
What's the functional form of the nonlinear spring for the normal force?
It's, in this case, it's a cubic polynomial. So it's just penetration to the power 3.
Okay.
And then there's a velocity effect that's multiplicative. So at speed 0, you get the static force deformation relationship. Yeah. When you hit the ground faster, you get higher force.
And that's a hyperbolic tangent for the friction?
It's a hyperbolic tangent. Yes, that's what it is. Yeah. Yeah, it's a logistic function. Yeah. So for most applications, it's not really critical as long as you make it hard enough. But if you really want to simulate, real surface conditions or footwear conditions, then you just have to do some mechanical testing and measure those. Yeah. So important for a lot of applications that I have is that these relationships, these force deformation relationship and force velocity relationships for the friction, that they have continuous derivatives. So I can use gradient-based solvers. So basically that means that if you write the code, you have to avoid if statements. That's the safest way to accomplish that. Then we have to put the two together. We have to couple the muscles to the skeleton. And that really goes through this one equation here. That if you have a model of the skeleton and muscles are attached to it, then that implies that muscle length is a function of your joint angles. If you apply the principle of virtual work, so you have an infinitesimal change in joint angles, that gives you an infinitesimal change in muscle length. And then the amount of work done by the joint torques must be the same as the amount of work done by the muscles. And therefore, the joint torques are related to the muscle forces through this gradient. The gradient of the muscle length with respect to the joint angles. And those are the moment arms. So if you have this, all you have to do is take the derivative and you get the moment arms. I'll get to that in the next slide. Oops. So you need some sort of model to derive this relationship. And mostly that's done with geometrical models, and I tend to use software that's been developed for that purpose, such as Sim and OpenSim, and this is a picture from OpenSim. And you can attach a muscle to the skeleton, you can have it wrap around geometrical objects. And I tend to use models that people have already made, because that's quite a creative process where you have to go on the computer and model this muscle and compare it to anatomy textbooks or MRI or other data just to make sure that it's realistic. So that's one way of doing it. Another way of doing it is say, well, it's not that important that I have all these details. Let's just assume constant moment arms. And that means that your muscle length is a linear function of your joint angles. Essentially, your muscles are now wrapping around pulleys at each joint. Then you get constant moment arms. And the D1 and the D2, etc., are your moment arms. But you can generalize that a little bit more. So instead of a linear relationship, you can do a nonlinear relationship. And I use that quite often in 3D models where you need a little more complexity than just the constant moment arms.
Ton?
Yep.
Sorry, question. And maybe this isn't the right time to answer it, so feel free to defer it. But is there a reason why you feel it's important to, say, model the anatomical accuracy of how moment arms might change, but do okay with a simple muscle model, like with simple activation dynamics and simple force velocity relationships and so on? Like, do you have a way to, like, how are you weighting what are the important things to include
Sure.
and not to include?
So I like to stay as simple as possible. So this works for all my 2D models. It's good enough, I think. If a moment arm changes by 20% in the real world, I don't really care about it because I have other problems that are bigger. But in 3D models, I really felt like I needed interaction between the angles. So for instance, in the hip, you have some muscles that are internal rotators when the hip is flexed, and the same muscles become external rotators when the hip is extended. Then you need a nonlinear regression model. Otherwise, you cannot represent that. And that's an essential part of your musculoskeletal function. And Sim does that, of course, geometrically. And if I want to do the same thing analytically, I need something like that. Yeah.
Can I just make a comment on Max's question?
Mm-hmm.
I believe that the state of the art of the stuff that you're doing is at such a state that you do not know the sensitivities of various candidate things to include or not include in the ultimate results. So that you would like to say you put in all you need and no more, and you say I keep it simple, but you don't yet know which of these things you could truncate and which extra little thing you might need that's very important.
That's right. You can always do a formal sensitivity analysis, but really nobody does that. So it's all based on what you intuitively believe to be important. And yeah, that's a good comment.
Sorry, I must misunderstood something. So that is the kinematic, the actuation kinematic. So you just say, I have in my bone certain attachment points, and then you have a line of length that connects those points. Is that all?
That's all it is.
Okay, but then why, I mean, you can just, from any decent modeling package, you can just get those lengths, and then you calculate the Jacobian to all the lengths of all the actuators, and the job is done. What am I missing?
Okay, so very often to make realistic musculoskeletal models, you need to wrap these muscles around obstacles, around other muscles, around bones. You end up with quite a complex calculation on the right-hand side here, which involves iteration sometimes. It involves if statements to see if something is touching an object or not. And so that takes time, first of all, and it's may not be differentiable.
Okay, so you're saying you cannot analytically just write the length of a path depending on the geometry, and then you have to do that adaptation. Is that what you're saying?
That's only if it's just a straight line between two bones.
Well,
yes,
then you can write.
Then it's analytical. But if it has wrapping objects, then it gets more time-consuming, and it may not be differentiable.
Okay.
So that's why I like to use these polynomials. And I can actually fit this polynomial to data that I get from the geometrical models. So then I get the same answer, but I get it with a analytical differentiable function that can be computed really quickly. So this is like a surrogate model that gives me the same answer as the real model. So that's an approach that I use quite often.
Hey, Ton, I just wanted to point out that a comment on Andy's comment, on Max's comment, that there are more and more sensitivity studies being done, and if you want to talk afterwards, I can point you to sensitivity studies on moment arms, on calculations of muscle forces, and also looking at the parameters within these muscle models, like which parameters are most sensitive to calculating muscle forces.
Andy?
If there's no, I mean, if there's time, maybe he should have a minute or two sometime
Sure.
today in public rather than say. If there's time, it would be nice to have some of that in public rather than in the corner someplace between just two people.
That might be useful.
Yeah, okay.
You want to do that later on?
I mean, I don't have anything prepared. I can just
Okay.
point you to some papers.
Yeah. No, one comment on that is that I think it's you cannot say for a specific model these moment arms are good enough. I think it depends on what you do with it, right? If you're trying to predict maximal running speed, and it might be completely different than when you're trying to predict muscle forces during gait. So I think you have a specific project, then you have to do for that project, you have to do a sensitivity analysis probably, which nobody ends up doing, but I think it's good to think about. Okay, so if we put all of this dynamics together, we end up with 4 sets of state variables. We have generalized coordinates, generalized velocities, we have muscle fiber length, and we have active states for the muscles. And this is typically how I arrange my state vector. And then we also have 4 sets of state equations. First one just says that your derivatives of the coordinates are the velocities. This is the multi-body dynamics. Now note these joint torques here. I've now written them as moment arms multiplied by muscle forces. And then for my muscle contraction dynamics, I haven't written this ugly inverse force-velocity relationship, but that's in there. And then this is the activation dynamics. Okay, let's do a simple MATLAB simulation where we just do muscle dynamics. And you can find that on your in your folder as a muscle.m. I'll go through it in a little bit of detail in a little bit. So let's say you have a muscle that's attached at one point, and then at the other end you have a motor, and you have position control, and you can program any length profile as a function of time. And that's really how people study muscle mechanics in animal muscles. And I put in some muscle parameters, and this actually, I think it's a rat soleus muscle. So the fiber length is 1 centimeter, and then you have a slack length of the series elastic element of 2.5, and we have a maximal force of 1 Newton. And I put an initial condition in of 2 centimeters, so this contractile element is very long. It's about twice the length at which it can produce optimal force. And then I'm going to program this motor to start at 3.8 centimeters and then ramp up to 4 centimeters and then stay there. And here's the MATLAB code. It's 2 pages. So you have some model parameters, simulation conditions. I'm activating the muscle fully. So active state is 1. I'm not changing that. I'm just having constant activation. So I start my muscle length at 3.8 centimeters. I start my ramp at half a second after the simulation. I end it at 1 second. And then that's my lengthening speed. It's 4 millimeters per second. Initial conditions, duration. I'm using an Euler solver, so I have a time step. And then the actual simulation happens on the next page. I just use a for loop to do my integration steps. First, calculate the muscle length based on that programmed ramp profile that happens here. Then I calculate the length of the series elastic element. That's the length of the muscle minus the length of the contractile element, which is the state variable. Then this is my nonlinear properties of the series elastic element. If I'm below the slack length, I get no force. If I'm above the slack length, I make it quadratic. So it's nonlinear, just like real tendons and soft tissue are.
That violates your if-statement rule.
Yes, but this is just a tutorial demo. This is not real production code. No, you're right about that. Then I can do the contractile element. So the force-length relationship, that's the length-dependent capacity to generate force, is my Gaussian function that I mentioned earlier. And the force-velocity relationship, it's the force is now the force in the series elastic element divided by the activation and divided by the force-length relationship. That's that nasty inverse force-velocity relationship. So first I have to calculate this, and then here the actual force-velocity relationship. And there's another if. So if I'm above this point, I have this hyperbolic relationship. If I'm below this point, I'm at this hyperbolic relationship. And that's a model that came from Katz in the 1930s, and that's a model due to Hill, and that also came from the 1930s. All very, very old, well-established models. Then I do my differential equation solver step, and I store the data, and then that's basically it. So let's switch to MATLAB and run this thing. So all you have to do is type muscle, and then you end up with a figure. It shows some of the variables. So this is the input. That's that ramp profile that I programmed in my motor. Contractile element length, it started at 2 centimeters, and you see it shortening here. Now, why is it shortening? Yep.
This code doesn't include that damper which you mentioned earlier.
It does not. Because I have full muscle activation, I don't need it here. Yeah. If I had zero muscle activation, I would have trouble here because I would be dividing by 0. So it's shortening here. And it's shortening at its maximal shortening velocity because there's no force yet in the muscle. The tendon is completely slack, so the muscle fibers are shortening at their maximal speed, which is 10 fiber lengths per second. And in this case, that would be 10 centimeters per second. Then the tendon becomes tight. You start seeing an increase in force, a decrease in the contraction velocity, and it kind of reaches an equilibrium here. And that is your isometric contraction. Then when you stretch this whole structure, you see this sudden increase in force. That's called the short-range stiffness, and that comes completely from the series elasticity, from the tendon. So here you're only stretching the tendon.
Does some of that come from the passive properties of the muscle that you're right length?
Well, if you see the contractile element length here, it's not making that jump. So what happens here is you're stretching the tendon that increases the force. And to get this lengthening velocity, you need also that jump in the force because of the force velocity properties. So this is a very typical muscle mechanics experiment that they do in animals, and that you can use that to identify some of those muscle properties. Yep.
Okay, I may have just totally missed the point here, but we're stretching the muscle and the force is decreasing, so it's a negative spring.
That's right.
Isn't that a little disturbing?
So you would think that's unstable, and that comes from here. It comes from the force-length relationship. So once you get past this maximal force, if you lengthen those muscle fibers, they can produce less force.
So then we have to ask the question, in vivo or in real animals, are we operating in that regime, or are we always operating in the positive stiffness regime?
No, we're operating on both parts. So there are two reasons why this is not disastrous. First, you have a parallel spring usually that I haven't modeled in this example that goes across this contractile element. And then the second one is you have that force velocity property that when you have that instantaneously, it's always an increase in force. Then at a longer time scale, I guess you get a decrease again. But the short response is always an increase when you stretch. When I simulate, I never see instabilities.
Okay.
But I don't have a fundamental understanding of it.
You're missing the passive elastic component.
Yes, but the passive elastic, it depends on which muscle. For some muscles, it comes in right at that maximum, and then there is no decline. But for other muscles, it comes in later.
It's much smaller.
Sorry?
You still get an instability, it's just much smaller than what's killing.
You get a decrease. Yeah, yeah. But yeah. Max.
If Chris is concerned about not the simulation, but whether or not we're in trouble in vivo, there is short-range stiffness that people have measured in which I don't think is necessarily attributable just to the force-velocity relationship. And it seems like one of the problems is that the way in which we determine the force-length relationship is, put it a length, activate, do it isometric, new length, and that force length relationship we're creating is not the same as if you held it at one length and stretched it to a new length, where you can actually get an increase in force even though you're on the descending limb of the force length relationship.
Yeah.
So that aspect of the muscle model, although commonly used, is maybe not the most accurate representation of what's like in vivo. Is that, am I saying things you
Yeah,
agree with?
I totally agree. If you show this to muscle mechanics experts, they say, well, you're leaving all these things out because there's some history-dependent effects. And that force-length relationship that I model as a Gaussian, it comes from experiments that are very different from these ones. It comes from experiments where you hold the muscle at one length, you activate it, and you measure the force. Then you start over at another length, and you activate it, and you measure the force. And so that's a bit of an artificial condition, but I think it's all we have. I'm going to do something more interesting, and here I think we're going to take a few minutes at the end so you guys can experiment a little bit with this model. So this is a muscle that's now coupled to a knee extension task. So we now have a rigid body segment with mass and inertia. We have gravity, and we're going to make this thing kick. And let's see. The code is structured very similar as in the other one. So we start out with calculating the muscle length. Now in this case, it's not a function of time, but it's a function of joint angle. And RF is the moment arm. So when this angle increases, the muscle length decreases proportionally. It's a constant moment arm RF. Then we do the series elastic element exactly like before. We do the contractile element exactly like before. Then we calculate the joint moment, which is the moment arm multiplied by the muscle force. And I'm subtracting the gravity contribution because that works in the opposite direction. And then angular acceleration is just the joint moment divided by the moment of inertia. Then I'm integrating three-state variables now. I have the contraction dynamics and I have the multi-body dynamics with 1 degree of freedom. And other than that, it's exactly the same. And if you run this, muscle is maximally activated. We see exactly the same thing. I've started the muscle fibers very long, so they actually have to spend some time on taking up the slack. And that's this 60 milliseconds here before there actually is any tension in the tendon. Then this force goes up very quickly. But look what happens. Even though my control is perfectly constant, I have this enormous increase in muscle force and then a very big decrease again. So this is all due to muscle contraction dynamics. Activation dynamics is not even in here. It's all due to muscle contraction dynamics. So this gives you some appreciation for if you're directly connecting your controls to muscle force or joint moment, you're missing all of this. And these are real things that are properties of real muscles. I'm going to try some input from the people here. So what you have here is at 90 degrees, full extension. Takes about 200 milliseconds to reach full extension with this model. I go to MATLAB here. I've added actually a couple of lines at the end that you might want to type just to measure that. So here is you find the data points where the angle is greater than 90 point, and then you take the first one, and that's that index of the 90-degree point. And then I'm measuring the time at that point. So the angles are in column 2 of the data matrix, and the times are in column 1 of the data matrix. You see that here, time and angle. So you type those 2 lines, and when you run the program, it will tell you how long it took to reach 90 degrees. And then I would be interested in, if you want to optimize a soccer player or a football player, as they call in Europe, for kicking the ball, do they have to have a larger moment arm or a smaller moment arm than what I've modeled here? You could try that too if you want. But I think a constant change might be the first thing to try just to get some insight. So the moment arm is right at the top of the code. It's 33 millimeters. Does anybody want to guess whether a larger moment arm or a smaller moment arm gives you a shorter kicking time?
The optimum is not infinity or 0.
That's right. There is an optimum. Yeah, I've tried to make it somewhat realistic. We're not optimized for fast kicking motions, maybe. So maybe the optimum is not the need that we actually have. Maybe the optimum is a different need. Has anybody tried it yet? Let me run it. I did run it already just before. So it's at 205 milliseconds with this model. Has anybody gotten the shorter time yet?
205 is your physical, is your anatomically correct model.
Yes. As I have it here.
Sorry, can you just make that text a little bigger?
Okay. Don't know if this has an option to do that. It does, huh? Okay. No, not here. Sorry. You must log off to apply these changes? I don't think so.
Within MATLAB, there's
Oh, within MATLAB, okay.
in the Mac anyway, the file.
Fonts. sounds better. Okay. Is this okay? Okay. Anybody less than 205 milliseconds yet? And did you increase or decrease the moment arm? You decreased it. Yeah. So you could find an optimum, and then you can do some orthopedic surgery to create the ideal soccer player, I suppose. And that's some of those things can be counterintuitive, because most people will think, well, if you have a larger moment arm, you get a larger acceleration. But it's not that simple, because muscle have these velocity-dependent properties, and you have a larger moment arm. The muscle shortens at a faster rate, and that drops the force more quickly. So you really need to model this and simulate this to
Which way did it work out that to get a faster kick, you use shorter moment arm or bigger moment arm?
shorter, smaller moment arm. And it's
The tendon was very compliant. Did you change your answer?
if the tendon was very compliant, yes, I think then a larger moment arm could be okay, because then you can shorten the muscle before the tendon shortens. You get that catapult effect. Yeah.
So we're optimized a little bit more for strength than for speed.
That's what it looks like. Yeah.
And if you can change your moment arm so that it was long or short, that would be best.
And I think grasshoppers and insects like that have sort of mechanisms like that. And I know in sprinters it's known that the ones with shorter moment arms, they tend to be faster. Yep.
So this is a nice simple model, which is like a prototype for what. This is a nice simple model, which seems like a prototype for the kind of optimization Katya showed yesterday. And so, have you or anybody taken a model like this and done the sensitivity analysis in terms of what can you prune from the muscle models, and still get, say, the reasonable prediction of the optimal kicking time?
Not for this particular problem.
Or any simple problem.
Yeah, any simple problem. I'm fairly confident that this muscle model has only what's needed. It doesn't have things that are unnecessary. But I haven't formally...
But, for example, if you just put a force velocity curve in, how far off would you be in your prediction?
Okay, for this one, you'd probably be okay.
What if you made that linear?
If you made the force velocity property linear.
Like an electric motor model.
Yeah, you might still get the same answer. Yeah, yeah. The important thing is that there is a force velocity property. Otherwise, qualitatively, you don't get that insight. Yeah.
I would think, for example, for Katya, say in particular, if she's here, I don't know, that just putting in a force velocity curve in her optimizations might be a big step towards what you taught here.
To have a joint torque that depends on angular velocity.
A maximum joint torque
Yes.
that depends on
Yes,
angular
and people have done that, yes. And there is actually data in the literature on torque capacity of humans and how it changes with velocity.
That, would maybe take you halfway from
Right.
where she is to where you are.
Right. Although I was surprised with her sprinting simulation, how good it was, because I've done also some sprinting simulations, and answers were very similar. And I think it was because she formulated it as a submaximal effort problem. So the speed was given, and the joint moments had to be as low as possible.
She also picked weights based on running data in her objective functions.
Okay.
So there's some fitting, free fitting, if I understand it.
Okay.
Another
Yep.
question?
Yep.
I'd like to make a model more complicated. What changes when you change fiber type?
Okay, so human muscles are usually mixed fiber types, and so I take an average of the properties of both. What changes is those time constants for the activation dynamics. They get faster for fast twitch fibers. And what also changes is the maximal shortening velocity parameter. Go back to this here. So this one here, this maximal shortening velocity, I use 10 fiber lengths per second. If I want to simulate sprinting, I don't get very good performance with this muscle model. I need to increase it to 12. And then I get a decent running speed. So fiber type is really important for this one. For walking, you never get even close to this, so I don't think it's that important. Does that sound okay?
So in walking, your knee actually moves quite fast in human walking, but it's not very powered.
In the swing phase, you mean?
Yes.
Mm-hmm. Right, so in the swing phase, your muscles don't really contribute that much, so muscle properties aren't terribly relevant. The forces are very low.
For your various parameters, like what would be for the quads or for the
yes, that's a good question. I was going to get to that in my full body model that I'm presenting. Maybe it's better to wait with that. Okay, so we've seen a little example of how you can play with design parameters and affect performance. I'm going to talk about the musculoskeletal model for Gait now. And that's something that has been in development for a long time, and it's essentially still the same model. And here are a few papers where I've used it for skiing, for Gait, and then the more recent one also for Gait. It's all basically the same model, but slightly different versions. And you have a folder called Gait 2DE 1.1, which has all these files in it. It has the model. It has, you have it in tutorial 2. It has the model. It has also detailed documentation, which is the PDF file. It's 25 pages, and it tells you all the model properties, and it also describes all the software. The model itself is coded in C, and it's been compiled into a MEX function, and I have versions here for Linux and for Mac 64 bits and for Windows 32 bits. If you need another version, I can give you the C code and you can compile it. I prefer not to distribute the C code because I don't want people to start making their own versions and then we don't know what version is what anymore. I am considering making this an open source project so that we have one place where we make new versions and people can contribute so we don't have lots of versions floating around and we can centralize the development. So if anyone is interested in helping with that, please let me know because the C code is there and it's fairly well documented, so it should be possible. I just don't have the time to support an open source project, so I need help with that. There's some application software. These are all M files that we will get to in a little bit. So the multi-body system has 7 body segments. It has mass properties and ground contact, deformable ground contact, as I've described before, 9 degrees of freedom, which are these, generalized coordinates. So the first 3 are position and orientation of the trunk segment, which is the root of the hierarchy. And then we have 3 joint angles in one leg and 3 in the other leg. I generate equations of motion with a piece of software called AutoLev, which does symbolic derivation of equations of motion. And then it spits out a C code, which I can then link to my MEX function. Yep.
So I'm imagining that you use AutoLev because you have used it for a long time. And if you were, that could be wrong, but if you were just starting now, would you recommend AutoLev, or is there some other package that you would use instead?
AutoLev doesn't exist anymore since the end of last year. So that's been taken over by another company called Motion Genesis. And they, I think I would still recommend it if you're a mechanical engineer. It's a little bit of an effort to learn it. but you really understand your system, the forward kinematics and the dynamics. And for me, AutoLev is really good because it gives me additional capabilities, such as symbolic differentiation. So I can generate code for my Jacobians, which I need in optimal control. So if...
Nowadays, just listening to people in this audience, I'd say young people tend to use ODE. Is there anyone who's used ODE and AutoLev or to compare or something like that?
Yeah, ODE, that's a good point. So I looked at ODE a few years ago, and I was a little worried that it's really only meant to do forward simulation. It's not meant to define state variables in a way that you can, formulate your state dynamics. And there are some ODE users here, I guess. But I wouldn't be comfortable using ODE for optimal control, for instance. Any comments? Yep.
So, AutoLev and something called SD-Fast are very different from ODE because they generate seed codes that does what you want. And typically they generate all kinds of seed codes, things that calculate Jacobians, inverse dynamics, forward dynamics, inverse kinematics. You get many, many functionalities.
Yep.
Something like ODE is meant to be a system that you sit in front of and use to a single purpose.
Yeah.
So they're really apples and oranges.
Yeah, I think ODE is a simulator, basically, and it's not dynamics.
The biggest difference is that ODE uses a maximal coordinate Cartesian representation, while AutoLev and SD-Fast use joints. I think that's the biggest
That's one big difference. Yeah, it's also a good point. Yeah, I've used SD-Fast. I only started using AutoLev maybe 4 years ago because I started doing some work for companies that need models embedded in their products. And SD-Fast, they wanted $5,000 for each runtime license. And AutoLev says, we don't care. You just generate the code and you can use it wherever you want to. So that's another issue. So the muscular system is this muscle model that has the small amount of damping in there in case you have no activation and you want to avoid the divide by zero. And then there are some muscle properties. And so where do I get these from? We originally started with, there is a book called Multiple Muscle Systems that was published in 1990. There was a symposium on musculoskeletal modeling. And there's an appendix, and that has lots and lots of these kind of numbers for all the muscles in the body. So that's one good source. But you can also hunt through the literature and find some of these as well. Yes? The name of the book? Yeah, it's called Multiple Muscle Systems, and the editors are Jack Winters and Savio Wu. So you might be able to find that book. There are also articles where people measure moment arms. So these are the moment arms that I've used, and they come from various articles about the lower extremity. There are quite a few sources that you can find. That's for this 2D model. For the 3D models, I tend to go to OpenSim, because OpenSim comes with a 3D musculoskeletal model that other people are using, and so I think that's a good thing to use as well, because then you can cite that and everybody knows which model you're using. So with more complex models like these, it's really important to kind of reassure yourself that you've generated a model that somehow represents essential properties of people. And one thing that has been studied a lot in people in sports biomechanics and in exercise science is strength curves. So strength is just the maximal joint moment that you can produce at a certain posture. So you strap a person in a machine where the joint angles are fixed. Then you tell them to maximally try to extend the knee, for instance, and you measure how much force it takes to hold them there. And that's your maximal isometric joint moment. So I can do exactly the same with this model. And I've given you some code. There's a test.m program that has various options, and one option is isometric, and that produces all these plots. And so, for instance, here is the hip joint, and I have positive curves and I have negative curves. So these are the flexors. Let's see. Yeah, these are the hip flexors, and these are the hip extensors. And you can see the hip extensors, they can produce something like 300 Newton meters. And this is as a function of hip joint angle. And then also as a function of knee angle, because there are two joint muscles. There are muscles that cross the hip and the knee, the hamstrings particularly here. And so their length depends on the hip angle and the knee angle. And so that's why you get these curves. And then you can go to the literature, and this is an article that I like to use, Kulig, Exercise Sports Sciences Reviews in 1984, that has strength curves for lots of joints and lots of directions and conditions. And then you can sort of reassure yourself that you're not too far away from reality. And same with the passive moment. The passive moment is where you just strap the person in and you tell them to relax, and then you measure how much force it takes to hold them there. And especially for the knee, if you try to go past zero, that's hyperextension. You see quite a large passive moment that I have in the model. And that reassures me that the knee won't go to the wrong side of the zero unless I apply a very large torque. So those sort of things are important. Yep. That's right. So there's also, if you run this test program, there's also isokinetic, and then you get these curves, but on the horizontal axis will be angular velocity. So you have that code to do that.
So in your model, you have like this kind of like four lengths relationships, and you have like
yeah. So this is So the muscles have all the properties that I've described, and then when you put it in a whole system, this is what emerges as the resultant of all of that at one joint. Yeah. So these are the effects of all the muscles combined. I think I modeled this here. It's in the documentation, but I think it's a quadratic. It's an additional joint moment that's a function of angle. It's not. Part of it is in the muscles because the hamstrings contribute to this as well. They have a passive elastic element. But it's mostly that additional passive constraint, yeah. It's good to have those mechanical constraints because then your model won't do anything weird no matter what your controller is doing.
Has anybody taken this and then just made a multidimensional force velocity representation of it? So rather than at a joint level putting force velocity, at a multi-joint level making force velocity.
At a multi-joint level.
So you take into account your the multi.
From a model or from real people?
Either from the model or from real people.
So for real people, I've done some experiments with real people that are actually have gone into these models, and those protocols are very difficult because to span like two joints, for instance here, you need to vary the hip angle and the knee angle. So here you already have a grid of something like 25 or 30 contractions, one for flexion and one for extension. You have to do that over several days because these are all maximal contractions. So these are very difficult protocols. And then if you also want to vary the velocity, you can imagine that it grows exponentially. So it's difficult, yeah. So people haven't really done much of that. Yep.
Are you talking about doing it on people? That's what you're saying? Yeah.
This was like 15 years ago. We did some with a Biodex or a Cybex, and you can test strength at different joints, put them in different postures.
That's usually one joint at a time, right?
It's one joint at a time.
But you're describing something where you're doing two joints?
No, you're changing the angles in two joints, but you're measuring the torque at one.
I see.
Yeah.
Is that what Andy was asking about?
Well, Andy was asking about the multidimensional torque, angular velocity relationship, because these torques, here I've only showed the dependence on two angles, but they also depend on both of those angular velocities. So you really have a very high dimensional relationship.
Okay. Thank you.
Yeah. Okay. It's time to get
Just a short comment on that. The most we are doing that since many years now, to trying to figure out muscle properties with using different setups and dynamic and static arrangement. And one of the major problems is the activity of the muscle. Let me see, you can measure it, but so they have the question is we assume in all our calibrations maximum activity, and nobody knows exactly what that is. So you get a rough number, but
yes.
you know exactly, you relate all this property to certain activity of the muscle, and this is still a major problem.
It's a major problem in these human experiments, because you can tell them to do maximal effort,
yeah.
But I'm not sure they always do it. And I think, especially in these machines where they're strapped in, it hurts to do maximal effort. So I think they might do a little bit less than maximal effort at their optimal posture, and then a little bit more at the other postures. So you really get a distortion, I think, of these muscle properties. Yeah. And sometimes I think it's even better to use the theoretical models based on muscle physiology instead of measuring it in real people. Okay, I suggest that everybody starts the GUI, and this is a GUI that runs a real-time simulation of this model, and you can control it interactively. So just type the word GUI in MATLAB. What will happen is this thing will fall down because it's not controlled. Let's try this here. So it looks already quite human-like, even with the passive properties of the muscles and the joints. And no, this uses ODE 15S in MATLAB, so it's an implicit integrator. I think it's a backward differentiation formula, I think. Yeah. And that turned out to be the fastest one for this model because of the numerical stiffness. And then you can, every time you click on each of these muscles, its activity goes up by 10%, and then it decays again by at a certain rate. So you see, when it's red, its muscle is maximally activated. So this gives you some kind of feel for what all the muscles are doing, and that gives you some confidence that we've modeled something that's like a real person. Now, you can't make him stand up with this. So I have this button that says bungee, so you can assist him with a bungee. And then you can play with the muscles again. So let's see. I'm going to try some knee extension here. So I've extended the blue limb now. I'm going to do the same with the right leg. There we go. You can get an appreciation for how hard it is to control something like this. The other thing I have is you can plug in a controller. So there's an M file that starts with the word controller. Then you can plug that in. And so here's, for instance, a controller that just activates the muscles at 50%. It's a very simple controller. This is what that does. Just makes the whole thing rather stiff. I have another one that does a really simple reflex loop. So I have the knee extensors are now being controlled with linear feedback from the knee angular velocity. That's the reflex demo. Now, that doesn't do much until you... Let's see. I need to crank up the gain a little bit. because you can get oscillations. It might. That's right. And you could also, if you want to simulate hopping and you don't want the balance problem, you might want to replace the bungee by something that constrains it vertically. Okay. Let's open the controller here. The reflex demo is here. So I take the knee angular velocity on the right side and on the left side, and then muscles 4 and 5 are my right knee extensors, and muscles 12 and 13 are my left knee extensors. I say all my muscles are, the controls are initially 0, and then I say I have a gain of 0.1, multiply by the angular velocity, and I don't want any negative controls. But I'm going to... Oh, because, stretch reflexes are typically thought to be driven by velocity. And I did angular velocity rather than fiber velocity because angular velocity is a state variable, so it's easy to get. Muscle fiber velocity is the derivative of a state. So I've multiplied the gain by 10. Let's see if that does anything more interesting. I need to load the controller again. Oh. What is it doing here? Bungee. Okay, you see these knee extensors now, they're flashing on and off. So now you have a high gain, and it's probably going to be chaotic forever. You see how these knee extensors, they keep... Yeah. So those sort of things are quite easy to do. Okay, let's turn the bungee off. And he's just lying there twitching. Yep.
Reflex delays?
I've never modeled that. No. You could, I suppose, you could do that here.
I don't know how to do it with a variable time step solver.
Yeah, I don't know that either.
Yeah.
There may be other people here who know that. Okay, and then the third controller I have is an open loop walking controller, which I obtained from Optimal Control. So this was the Optimal Control work that I've cited, Ackerman and me, was published last year. So that's just controls as a function of time that gives you a walking pattern. But of course, when you run it through here, it will fall apart pretty quickly because the system's unstable and there's no feedback. So let's load that one. And I have an error. Let's try that again.
Oh. So is it easy to implement external forces, say joint torques or the bungee?
Yeah, good point. Good point. Let me show you how that's done. Okay, so just quickly, we have 50 state variables in this model. The multi-body dynamics and the muscle dynamics. There's 16 control variables because we have 16 muscles. And this is just a little bit of an interactive of how you use that MEX function. The whole dynamic model is in a MEX function that basically computes this function. So if you give zeros in all the states and zeros in all the controls, then your X dots are going to be looking like this. For state 15 and 18, I get extremely high state derivatives, and it's because these are the ankle angular velocities. Where ankle is very far below the ground, we get very high ground reaction forces, and so that's a very high angular velocity. It's just to show a little bit of understanding of what this does. And the full specs of this MEX function are in a file gait2de.m. And you see on the right-hand side, I have states, I have controls, and I have extra inputs. Those are my additional actuation. If you, for instance, if you wanted to model an orthosis that generates additional moments that are not muscles, you can input them there. And then you could wrap this in another function that generates some muscle controls and some orthosis controls if it's an active orthosis. This is also where I put the bungee force, because the first three generalized forces, they act on the trunk. And so the bungee was also input that way. So you have, and if you wanted to model a robot with no muscles, you make all these muscle controls 0, and you only input the torques there. So you can do a robot as well. On the left-hand side, you can get state derivatives, but you can get optional outputs like ground reaction forces, stick figure, data structure, muscle forces, and joint moments. And if you want other stuff, we'll have to go in the C code and add those features. So here's a basic simulation application that you would use for offline. So the GUI is kind of fun to play with, but for more serious work, I wouldn't recommend it. So here's just a skeleton or a basic structure of a simulation application for offline simulation. So some constants, number of degrees of freedom, muscles, and states, an initial condition. I created this posture just by manually inputting some coordinates and angles. Within X, I have some muscle fiber lengths, and I set them all to 1.4, which is long enough that you don't start out with this high tension in the tendon, because if you start out with that, you get this catapult effect, and you don't get very interesting movement. So, and I've done that in the other simulations as well. Then some duration, how often do I want to see output? Just the setup, and then to run the simulation. Now here I used a Runge-Kutta variable step solver, ODE23. You have to give it your differential equation function, your time grid for your output, and then your initial state. And then when it's finished, I have a little function anim that creates a stick figure animation. And in this case, I was interested in making it jump, so I'm also printing the maximal hip height, which is state variable 2, and I'm just giving the maximum over all the time steps. So your differential equation is x dots as a function of t and x. So the first thing is you use a controller to generate the controls based on time and state, and then you just input that into the model, and the state derivatives come out. And the controller here, for jumping, I just activate all the muscles maximally and see what happens. Okay, back to MATLAB. So it jumps a little bit and falls on its face. And then, of course, my challenge to you is, can want this controller so it jumps a little bit higher than 1.1397 meters? Any ideas for how you might want to try to get it to jump higher? Yes. Yeah. Yeah, preload, but that's I don't think that's really fair. I mean, you could, yeah. That's what I said about the catapult effect. You can store elastic energy and then just make it jump as high as possible. Anything in the controller you can think of. Oh, what did you say, Andy?
Turn off the antagonist.
That's right. That's the very first thing. Yeah. Oh, Andy said the first thing you can try is turn off the antagonists. So I've activated all the muscles, but not all of them contribute to leg extension. There are flexors as well. So if I wanted to do that, Maybe some of you can try some things while I'm trying this. Okay, so in the one you have on your flash drive, I've actually listed all the muscles here, the 16 muscles. So some of the flexors are iliopsoas, that's number 1. And then we have tibialis anterior, number 1 and number 8, and 9 and 16. Those ones should probably be turned off. Okay, let's try that. One, 8, 9. Okay, now I've turned off those 4 muscles. That's pretty good. It's 15 centimeters higher. So what's the next thing you might want to try?
Can you co-contract and turn off the
F-min-con, there you go. Greg said co-contract and then turn off the antagonists. So first you activate all of them and then you turn off the antagonists. The other thing that people have tried is to not turn on all the muscles at the same time, but in a certain sequence. So you can play with that, and of course you can parameterize a controller and then run an optimization to get the maximum jump height. But before you get too excited about that, let's go back to the slideshow. So you need to be careful with your initial conditions because that may affect performance. And I think it should be in an equilibrium if you want to do a fair starting point. So you have to be in equilibrium. And there's lots of previous work on this problem as well that you should look up. I think one unsolved problem is the squat jump versus counter movement jump. So if you start out from a standing posture, the optimal strategy should be to go down and then to go up. And whenever I've tried that, all it did was this. It never found this and then this. So that might be an interesting optimal control problem to work on.
Your optimization never found the counter movement.
No, this was a while ago before I did the direct collocation, so it might still be possible. I don't know.
So is it correct to say that muscles are not springs? The surrounding tissue and the tendons of the spring part, that's what stores energy? What is the parallel elastic element?
That's a spring too.
Is that muscle actin myosin, or is it just
It's just tissue that's around the actin myosin.
So when we talk about energy storage in running, let's say, we're really talking about energy storage in passive tissues. In these models, there's no energy storage in the contractile element. Is
No,
that
it's
right?
in the series elastic element.
Which tendons?
Which is tendons and muscle fibers are usually much shorter than the muscle itself. So you have series elasticity inside the muscle as well, which I all lump into that one series elastic element. I don't call it tendon. It's everything that's in series with the contractile tissue.
Now, at a psychophysical level, you can ask people to contract their muscles and you can give them perturbations. And from the outside, it looks like their stiffness goes up. And I would argue it's much bigger perturbations than short-range stiffness. Where is that coming from?
Okay, that's because the series elastic element is nonlinear. So you can change the set point by generating more or less muscle force. So if you have no muscle force, you have no stiffness. If you have high muscle force, you go higher up on that force deformation curve of the series elasticity, and it becomes stiffer. It's the nonlinearity of the elastic elements.
Did he not have said yes exactly that?
I think he's happy with it.
So what about Titan?
Yes, I lump that into the parallel elastic element as well. So there's a protein inside the muscle that sits between the sliding filaments. It's titin. It's also parallel
And there's
elasticity.
some evidence that Titan's stiffness is dependent on activation. So it's not
Okay, so it's not passive. It's not entirely passive. Yeah.
That's still not clear.
Okay. Yeah. I think we're getting to the end of the tutorial. So just want to talk a little bit maybe about further work that you might do with this model. So you can, you could take my open loop controller and try to add feedback. You could try to make it walk with a reflex-based controller. You can try doing optimal feedback control or even stochastic optimal control, which I'm really interested in, but I don't really understand the methods yet. But, yes?
So this thing can actually walk as it is packaged?
This thing can walk, and I wasn't able to do that demo because it crashed. Let me try this again. I load the controller, the open loop walk controller. Yeah. This happens sometimes, and I was always able to fix it by trying it again, but okay. Something has to go wrong. But you can load that controller, and it has pre-programmed controls as a function of time for a normal gait cycle. And that was, the cost function that was minimized was based on tracking real human gait data, joint angles and ground reaction forces, and also a minimal activation squared term. And it walks very realistically, but it's not stable. So yes, this thing can walk if you control it right. Yeah.
Your ground contact model keeps track of where the points intersect the ground.
Yes.
Don't those points need to be part of the state then? We weren't able to see in the code where those points are kept track of.
So the points are attached to the foot, and so their coordinates are a function of state variables.
Sure, the points on the feet, but don't you need to know where they first intersected the ground so that you can connect your springs between those points?
No, not because in the horizontal direction there's no elasticity. It's only friction.
Oh, okay.
Yeah.
Right. Okay, and you know where Z is 0. Okay, thanks.
In terms of the software you've showed us so far, what else is there between what you showed and the optimization?
Not that much. I mean, if you read the article that we published last year, there's a few steps that you need to do to discretize your dynamics on a time grid, and then you throw it into a nonlinear programming solver like SNOPT, and the gait pattern comes out. But that's easier said than done.
But which of these subroutines do you not use or do use?
I use the MEX function, the dynamics, and then you approximate the derivative with some finite difference, and that becomes your constraint at each time interval. And then you have lots of those constraints. You have one for each time interval.
Ton, following up on my earlier question about, which parameters matter, and, what was brought up was about sensitivity analyses and so on. And I guess what I want to know is, like, in a way, you've been doing sensitivity analyses for your whole career doing this. So you have some collective knowledge about what's important just by your experience with doing this so often.
Right.
So what I'm hoping you'll share with us is your, unproven but nevertheless probably fairly firm beliefs about what matters and what doesn't matter. Mm-hmm. So maybe beginning with the muscle mechanics, what do you think matters, what doesn't matter?
I'm not entirely sure about everything, and when I'm not sure, I put in a little bit more complexity than what I think might be necessary. So, but I'm confident that this model that I'm presenting here, it has the essential things that are needed for walking dynamics, but maybe a little more than what's needed, but not too much more. So you can look at the description of the model, and that gives you kind of a good picture of what I think is important.
And within that, there isn't like you particularly care about like slack length or the moment arms or is there or the ground contact model? Like,
so
aren't there things that you really feel like you have to get right?
Yeah, the slack length is a good one that you bring it up, because that's the slack length of the series elasticity. And if you change that, you change the strength curves, because that shifts them horizontally. So that's one place where you can look at human data and say, well, which slack length do I need to get my strength curve in the right place? And then that's the one you use. Actually, I do it the other way around. I take a slack length from actual anatomical data, and then I change my length-angle relationship for the muscle path to shift that. Because it's important you get the strength curve in the right place. So, but you cannot really change the slack length by 50% because then your series elasticity gets too stiff or too soft, and it's not realistic anymore. So yeah, it's really hard to summarize that, I suppose.
Yeah, let me try one. Let me try one more way, which is so, you're allowed to ask of an experimentalist who has unlimited resources and skills to do one experiment that will tell you one thing completely accurately. Mm-hmm. Which is it that you would use in order to gain better confidence in what you're doing? What experiment would you like them to do? What is the parameter you're least certain of? And that is really sensitive to.
One parameter that this model is sensitive to?
And more, not just this particular model, but in your experience, like, do you really wish that people would give you better numbers for...
Yeah, I mentioned the sprinting, and it was really sensitive to the force-velocity relationship. Yeah. And so what I did was I just increased the width of that force-velocity relationship until the model could run 9 meters per second. That's not really a good way to do it. I would like to be a little bit more based on muscle mechanics experiments. So that's maybe one.
So we have a small problem with time.
Yeah, we should eat.
Is there some more question?
I was going to follow up on Andy's thing. So there was a nice publication by Friedel van de Groot at KVU Leuven that looked at the muscle parameters max that showed that the muscle models are very sensitive to the tendon slack lengths, and they looked at all of the different, a bunch of different muscles in a model with like 16 muscles, and that's published in Journal of Biomechanics in 2010. There was also, Jeff Reinbold did really good work looking at when you're doing inverse dynamics and calculating torques, what's more important? Is it the mass properties, or is it the joint centers and joint axes in your model, looking at subject-specific stuff? Yeah. And it showed that it was really important to get very accurate joint centers and joint axes. So that's another type of study I was referring to that can show you like what's important to models.
Yeah, so it shows you that it depends on what you use the model for. For the inverse applications, I think muscle properties are not terribly important for walking at least, but it's more important that you get your skeletal system right. And then for the forward dynamics, maybe things like force velocity properties, and when you go to fast movements, it becomes really critical.